Let's talk about Indian mathematics. Again, in the span of 20 minutes or really several hours, I will not be able to really comprehensively cover it, so we will just highlight some of the main achievements here. Indian mathematics was very impressive very early on. So in between years 33 and 1300 BC, we already see some very deep mathematical reasonings and constructions. Bricks, whose dimensions were always in the proportion 4 to 2 to 1, because that was favorable for the stability of a brick structure, standardized system of weights that are based on various ratios and actually producing in mass those weights of regular geometrical shapes. So the ability to do so with high precision. Standardized measurement of length with a ruler, and the unit length being 1 finger, an ability to measure a variety of angles in a plane, determine the position of stars for navigation, and so on. Some of the most interesting things are the oral tradition of the Indian mathematics, and in fact, this is a hail to big numbers. And if you look for it, you will find it very, very quickly. Hail to Sada, 100, 1,000, 10,000. At some point, the numbers actually do begin to mean things, and I encourage you to look up the various meanings behind them. Once you get into the really big numbers, the ocean, the middle, the and, beyond parts, the universe. Hail to the dawn, to the twilight, to the one which is going to rise, to the one which is rising, to the one that has just risen, to the heaven, to the world, hail to all. This kind of prayer, this kind of thanksgiving is actually present across many different cultures. And this reminded me of the Haudenosaunee prayer. And I'm going to read a quote from Rod McCormick, a Mohawk professor at UBC and now TRU, about this expression of thankfulness at the opening of an Aboriginal gathering. He says, the expression all my relations in many ways encompasses the Aboriginal worldview and a pan-Aboriginal definition of interconnectedness that we as Aboriginal peoples have with family, community, nation, and creation. It is a clear declaration that we're all in relationship with one another in this world. In using an example of this teaching from my own culture, Haudenosaunee, the proper way to open any gathering is to recite a Thanksgiving address in which our world is thanked as relatives. Those relatives may include Mother Earth, Sky Father, Grandmother Moon, and our brothers and sisters in the plant and animal regions. All my relations also encompasses the spirit people, those who came before us and those not yet born. It is an affirmation of our interconnectedness to all of creation. End of quote. And notice that after each thanks is given, everybody is reminded that now our minds are one, emphasizing that we are, in fact, part of one whole. Mathematics is only one of the expressions of culture that we can trace through the world and through time. And this is a mathematics course, so that will be our focus. But as we go through, look out for other opportunities. Look out for other ways that each culture is unique and each culture is wonderful in its own way. Back to ancient Indian mathematics. The Hindu-Arabic system is, of course, the number system that we use today, and it originated in year -300. They already had the place value system of using symbols 0 through 9, and placement of them is what corresponded to their actual value. The use of 0, that is also referred to in Chinese manuscripts in year 718, was used in the Hindu-Arabic system. The number system has progressed from the Brahmi numerals that were there originally to the variety of representations through the years and has settled on the thing that we're using now in the 16th century. The sources of Indian mathematics, we have a couple of, one of which is Sulba Sutras, which dates back from somewhere between 800 and 200 BC. So again, this has various editions, various copies and commentaries and so on. This describes the construction of fire altars and ritual arenas. The constructions of fire altars were very specific. They had to satisfy certain rules, which made it quite a difficult task. They must have different shapes but occupy the same area. They consist of 5 layers of brick. Each layer has to have 200 bricks, and no 2 adjacent layers can have the same arrangement of bricks. This already seems like a very difficult problem, but on top of that, different shapes of altars also corresponded to different requests for the gods. For example, the falcon was for those that desired heaven. A rhombus was to destroy enemies. A bird was for wealth, and so on. So you can see immediately from these requirements that mathematics, and quite serious mathematics, and understanding of not only shapes but also patterns of numbers was necessary for these constructions. The great advances of Indian mathematicians also consisted of the earliest extant verbal expression of the Pythagorean theorem. And some researchers believe that Old Babylonia got the theorem of Pythagoras from India, or that Old Babylonia and India got both some third source information, potentially predating the year minus 1700. The earliest recorded usage of a circle character for 0 that we use to this day is due to Indian mathematicians. The approximation of root 2 as a basically series, except for finite in this case, is correct up to 4 decimal places. We see lots of combinatorial counting and combinatorial identities in Indian mathematics, and that is possibly motivated by the things like the constructions of the altars that have a lot of number patterns embedded in those requirements. Some of the most important figures in ancient mathematics in India is Ari Para, that lived in around 500s. Some of his main achievements were approximation of pi that he actually lists a procedure of in terms of a circle. Solutions to first-order Diophantine equations. Diophantine equations are the equations that have solutions as integers. So anything of this form, he actually gives a very precise algorithm to do so. And then finally, various combinatorial identities, the summations of this series that can be visualized as patterns of numbers as well as through the actual shapes. Ari Para also studied astronomy. He scientifically explained solar and lunar eclipses. He calculated the side real rotation to be almost exactly the same as the modern value. So he calculated to be 4.1 second. We are just barely under that. Estimated the circumference of the Earth to be 70 miles off of its true value. That's crazy. The definition of sine and cosine gave birth to trigonometry in the same way that some of the Greek mathematics did. And India's first satellite was named after Ari Para, as well as a lunar crater named in his honor. Another very big figure in ancient Indian mathematics is Brahmagupta, that lived after Ari Para, so in the years approximately 600. He also has established a number of really deep mathematical results. For example, mathematical rules with dealing with 0. What to do when a number is subtracted or added or divided or multiplied by 0. 0 became an actual abstraction to be understood, not just a place value to separate numbers such as 20 from the number, 22 or something like that. He established rules for dealing with negative numbers in the same way as with 0. So here you can read through how he actually phrased those. A debt subtracted from 0 is a fortune. A fortune subtracted from 0 is a debt. Fortune is a positive number. Debt is a negative number. Thinking about it in terms of money worked for ancient India and still works quite well today. He gave 2 equivalent solutions to general quadratic equations, noted that quadratic equation could have negative solutions, something that a lot of ancient mathematicians have ignored because negative numbers overall are not a concept that one thinks about when counting real physical things. Solve quadratic equations with 2 unknowns, which was not done in the West until 1,000 years later by Fermat, and gave the area of a cyclic quadrilateral with sides A, B, C, D, and semi-perimeter S over here. Let's take a look at a geometric result known as Brahmagupta's theorem. So what we have here is 4 points on a circle such that the lines AC and BD are perpendicular. We're going to denote the intersection of those two lines by M, drop the perpendicular from that point M onto the line BC, and name the intersection E. F is going to be the intersection of the two lines that are formed, and what the conclusion is that F is the midpoint of some line segment. Now, geometrical theorems are best visualized using geometric diagrams. So I encourage you to pause the video here and try to actually put this onto a circle and recognize where what points are, and then come back to the video. Now I'm going to cheat a little and present you with this beautiful diagram of my own. Hopefully you have something similar to this. So what we have to prove is that F is the midpoint of AD. So that means that it lies exactly in the center. And we're going to prove that, as Brahmagupta did, through a sort of third party. We're going to prove that AF is equal to FM, and then we're going to prove that FD is equal to FM. Because they're both equal to the same thing, they must be equal to each other. Okay, so first of all, I'm going to prove that AF is equal to FM. Now, what does that really mean? If AF is equal to FM, I'm going to then prove that this side is equal to this side, which means that the triangle that both of these sides live in is actually isosceles. So this angle is equal to this angle. That means that I can actually think about the problem of side equality in terms of the problem of angle equality. And angles, there are abundantly many in this circle, so this gives me a lot more flexibility about how to reason. So first of all, let's focus in on this arc, CD. I know that angles that are supported by the same arc are equal in measure. And remember, my final goal is to prove that these two angles are equal. So these two angles are something that I have to connect. Well, this arc actually is supporting this angle right here, this one that I care about, right? But this arc also supports this angle right here. So immediately, I know that these two angles are actually equal because they're supported by the exact same arc. Let's write that down. So what I have is that the angle that I can call CAD is equal to the angle that I can then call CBD, and I can give the justification supported by the same arc. And I can call the arc CD with like an arc over it. Okay, well, that's great. Maybe let me label them on my sketch here. I've proven that these two angles are equal. But again, remember, I want to prove that this angle is equal to this angle. So how can I find some other quality when it comes to this angle? This next one is a little bit, you might have to tilt your head around a little bit. My claim is that this angle is actually equal to this angle. Okay? And that is because if you look closely, this angle lives in this right angle triangle right here. And together with this angle makes up a 90-degree angle, right? This blue angle, this guy, together with this angle adds up to 90 degrees. But there's also another little right angle triangle here where the same blue angle and the exact same angle right here also add up to 90 degrees. Well, if the same angle adds both of these up to 90 degrees, they must be the same. So my next claim here is that this angle is also equal to EMC angle. EMC. And the justification that I will give here is that they both add up to 90 degrees with this other angle that is, say, ECM. Well, let me call it BCM to see that it's the exact same angle in both triangles. BCM. Alrighty, so now I have this angle. Well, the next step should be fairly straightforward to see. You can see these two lines, and I know by vertical angles that the angles on the opposite sides of intersecting lines are equal. So this right away gives me that this angle is going to equal to this one. So my next step is that this whole thing is equal to the angle AMF. AMF. And here my justification is vertical angles. Well, this is fantastic news because now I have that these two angles are equal, which means that this triangle is in fact isosceles. So I can say therefore triangle AFM is isosceles. Isosceles. Why can't I spell this? Let's pretend that this is correct spelling. It's isosceles. An isosceles triangle means that at the base, the other two sides are in fact equal. So this immediately implies that AF is equal to FM, which is what I've set out to prove in the first place. The second part of the proof will be analogous, except for we're going to prove that FD is equal to FM, and this goes very analogously, very similarly. So I encourage you to actually fill in the steps and reason out the exact same way, finding the corresponding arc, finding the corresponding angles to it up to 90 degrees to see that this is in fact the case. Now, once I have that, I have now proven that AF is equal to FM and FD is equal to FM, which of course then implies that overall, therefore, AF is equal to FD, and that means that F is in fact the midpoint of this region. Brahmagupta has a couple of really nice results when it comes to cyclic quadrilaterals. Cyclic meaning their four vertices lie on the circle, this being one of the nicest concisely stated theorems. Indian mathematics has a number of other very impressive works by other mathematicians that, again, we don't have time to go into detail about. But as you can even see by the years, while the Europe was going through the Dark Ages, Indian mathematics in many ways flourished. Bhaskara 1 and 2 did remarkable works extending Aryabhata's work. So rational approximations of the sine function, which really is like a table that one can use even today instead of a calculator to figure out the values of a sine function of various angles. Bhaskara 2 gave the first general method for finding solutions to what we now call a Pell's equation. And what is really interesting is he actually solved Diophantine equations of the second order, such as this equation right here. And interestingly enough, this exact equation was actually posed as a problem by Fermat in 1659 and solved by Euler only in the 18th century. He also conceived differential calculus after discovering an approximation of the derivative and differential coefficient, of course not using that terminology, by the various approximations and the sort of the method of exhaustion. Madhava in later years also extended this idea and introduced infinite series approximations for a range of trigonometric functions, building on much earlier work by Indian scientists. All of this 200 years before Leibniz did the exact same thing. Even gave estimates of the error term and used all of this to approximate pi to 13 decimal places. Incredible work being done in medieval Indian math. Take a look at some of these achievements, Google something, and find what interests you and what impresses you the most.